Hello and welcome to Power System Analysis 2. We are in module 2. This is the fifth section. Okay, in the previous modules we have talked about different load flow methods like Newton-Raphson method, decoupled method, and we have seen the fast decoupled method. Now in this section we are doing the comparison of the different methods. Okay, we'll see which method is suitable for what purpose, and after that comparison we'll be looking at the section that is called voltage control of the different buses. Now why this voltage control is important? Because we have seen with the change the relation of voltage is directly linked with the change of reactive power within the buses. So if the reactive power drops or reactive power rises, the voltage rises or drops as well. Now maintaining a voltage is an important factor in the power system control, because we cannot be like when we are when we have a voltage profile in the for every household as 230 volts single phase, so we cannot expect the voltage to drop to 200 or like 300 volts. There should be a certain amount of constant voltage in order for our appliances to work properly. So voltage control is very important. So we will be looking at ways of the how the voltage is controlled. Okay, so let us get into the topic. So in this first slide we are comparing the different load flow methods. So there are a couple of points, so I'll explain all of these one by one. It is experienced that the Gauss-Seidel method works well when programmed using rectangular coordinates, whereas the NR requires memory when rectangular coordinates are used. Hence, the polar coordinates is preferred for the NR method. So here we can say that the Gauss-Seidel requires the elements, the complex element to be represented in the rectangular coordinates in the form of a plus jb, whereas in the NR method it is helpful and it will require lesser amount of memory if polar coordinates are used, that is in terms of r theta. Okay, the next point, Gauss-Seidel requires fewer number of arithmetic operation to complete an iteration. With the NR method, the elements of the Jacobian are to be computed in each iteration, so the time is considerably longer. So in the NR method, the number of operations is larger because we are using the Jacobian with respect to the Gauss-Seidel method. So in the actual case, both Gauss-Seidel method and NR method is taken together. So the third point, the rate of convergence of Gauss-Seidel method is slow. The NR method has a quadratic convergence characteristic. Now even if the NR method it takes a lot of memory and it is much more a complicated method, the convergence, that means that is how fast the equation is solved, is much more faster in terms of NR method than the Gauss-Seidel method. For large systems, so we are in point 4, the large system, the NR method is faster, more accurate and more reliable than Gauss-Seidel method or any other known method. So for a large system, the NR method is much more preferable. The fifth point, the chief advantage of the Gauss-Seidel method is the ease of programming and most efficient utilization of core memory. Okay, so this is a very straightforward point. The NR method is decidedly more suitable than the Gauss-Seidel method for all but very small systems. So NR method is specifically much more suited for large systems. For small system, Gauss-Seidel method is preferable. The FDLF or fast decoupled load flow, the convergence is geometric. 2 to 5 iterations are normally required for practical accuracies, and it is more reliable than the formal NR method. So FDLF method requires a less amount of iteration, 2 to 5, and for the practical purposes, because we do not need that amount of accuracy, but we need to understand the state of the system. If delta P, second but last point, if delta P by V and delta Q by V are calculated efficiently, then the speed of iterations of the FDLF is nearly 5 times that of the formal NR method and about 2/3 of the Gauss-Seidel method. So this is the how FDLF is much more faster, we have just seen. The FDLF method can be employed in optimization studies. Okay, now what is this optimization studies? I'll just make a brief idea of these things. Now let me tell you, why do we require all these load flow studies, and what is the load flow study? Load flow study, as I've said from the previous classes, that it is nothing but it is a static study. That means it is not dynamic. It takes the static values of the present situation and it tells you how the system is working. Just imagine a power system to be a patient in the hospital. Okay, so if we wanted to know the condition of the patient, we look for his or her blood pressure or the different characteristics of the patients, different results of blood pressure, maybe his heart, how his heart is working, also all these values tells you how the system or how the patient is. Similarly, in the power system, we need to understand the power injection, the real power injection, the reactive power injection, the voltage angle for every bus. So, and we need to understand that is the bus system healthy? Is it working fine, or is there a problem in the bus system? So in order to find out the problem, so you can realize that we cannot expect every time to solve the equation you need a lot of time to get the condition of the system, because by that time the system may collapse. So we need to find a faster system to at least have an idea of how the system is presently working. Okay, so faster methods like FDLF is much more used. Okay, and there are again further more methods like the DC load flow, which is much more faster. Now, is it accurate? Absolutely not. It is not. You cannot get the exact solution, but it is an approximation that we can say, okay, it is working fine, but I'm continuously monitoring the system state. So you need to understand these load flows are utilized, and nowadays computers are there which constantly takes in values from the different buses, and regularly with a small interval it calculates the load flow in order to provide the operator the condition of the power system. Okay, so in order to know the condition, the data collection and the calculation should be faster. So most of the time these faster decoupled load flow methods are used. Okay, in the next section or next slide, we will be talking about the voltage control of the buses. Now, control of voltage profile. Now, before that, you need to understand what is a voltage profile. Voltage profile is the change of voltage from the minimum and the maximum, from minimum to the maximum. So what is the range of this voltage fluctuation? If the voltage fluctuation is big, then there is a problem. So in order to accommodate a small voltage fluctuation, we need some kind of method to stop it. Now you might ask, why do we need a voltage fluctuation? Can the voltage not be fixed to a particular value? It cannot be fixed to a particular value because the voltage is dependent mostly on the reactive power and partly on the active power flow. And obviously in the power system, the load is not constant. The load is random. You are switching on, switching off lights, and not only you, millions of people are doing in the same way, and nobody is bothered whether the voltage will fall or voltage will rise. Okay, so in the let's say for our JCE campus, during the class hours, all the lights and fans are on. So if you think from that point of view, the JC itself is creating a lot of load. Okay, but suddenly after 4 o'clock or 5 o'clock, when all the students go away, the powers are switched off, and during the night it is almost zero. So you can see how the load fluctuates, and due to this load fluctuations, you can have different amount of reactive and active power flow in the bus that is connected to our JCE college. Now due to these changes in the power flow, the voltage will change. The change of voltage cannot be stopped, but obviously it can be controlled. Now how it is being controlled, we'll be seeing. There are two methods of controlling, from the generator side and from the transformer side. Now we'll look for the generator side. So we are looking at control of voltage profile by the generator. Okay, so in the above diagram, yes, you can see we have a generator. Okay, that the generator has a voltage of EGI and with an angle of delta G. Okay, G represent the generator. Okay, so and it is connected to the bus with a reactance of XGI. Now from this bus there is a load. Load may be connected to the bus, and the voltage also provides both the load as well as the power system shown on as a bigger circle or bigger shape. Now this power system, this shape, you have to understand, this is a huge system. This is just a representation. So it's a power system. The bus is providing the voltage. Now how this voltage is generated, the equations are provided on the right. Okay, so PGI is how the PGI is calculated and how the QGI is calculated. So what is this PGI? It is the power flow, both real and reactive power flow from the generator to the bus. Okay, so from the generator to the bus. So the generator load angle is delta GI and the bus load angle is delta I. So it is the sine of delta GI minus delta I, the change in the bus in the voltage angle that represents the power flow from the generator to the bus. So let us look at the text. With PGI plus JQGI and modulus of VI angle delta I given by the load flow solution, these values can be achieved at the bus by adjusting the generator excitation EGI as required, and by adjusting the governor setting so that the power input to the generator from the turbine is PGI plus the losses, resulting the load angle delta GI minus delta I corresponding to equations that we have given. If QGI demand exceeds the capacity of the generator, VAR generator, that is the synchronous or static capacitor, has to be used to modify the local load. Now let me explain. Now what we are seeing is that this PGI and QGI is produced, and this PGI and QGI is not directly transferred to the power system because some of it is utilized for the loads. Okay, so it is along with the power system and the load, you can see the injected power of the to the power system is PGI minus PI plus JQGI minus QI. Okay, now this generated power can be changed in order to our requirements. Now how P is changed? P is changed by increasing the turbine speed. Okay, by adjusting the governor, the power flow from the generator to the bus is changed. By the how the Q is changed, the generated Q, it is changed by adjusting the generator excitation. So the generator, it is excited by the rotor of the generator excited by a DC power. So that DC power, the excitation, that being changed, the generated reactive power will also change. Okay, so these are how the generated reactive and real power is changed. Now what is the power that is transferred? It is depending on the angle of the between the generator delta and the bus delta. Okay, now if the demanded reactive power exceeds the reactive power that is being capacity, that is beyond the capacity of the generator. Let's say the power system on your right demands a lot of reactive power, okay, because a lot of reactive power elements are required. Let's say if the power system has a lot of induction motors are hungry for reactive power. If a lot of reactive powers are required, what will happen? The voltage will drop. Now in order to compensate for the reactive power, the excitation should be changed to produce this required reactive power. Now what happens is that if the generator is not able to provide the reactive power, we need to connect to a synchronous or a static capacitor to provide that reactive power. So in the next paragraph, it follows from the above that the control of the voltage profile of an interconnected system, buses with generator are usually made PV buses. So control of the voltage profile of an interconnected system, the buses with generators are usually made PV. So when we have a controlled reactive power, that the bus is considered to be a PV bus. Load flow solution then gives the voltage level at the load buses. If some of the load buses work out to be less than the specified lower voltage limit, it is indicative that the fact that the reactive flow capacity of the transmission line for specified voltage limit cannot meet the reactive load demand. So if there is a voltage drop, that means the reactive power demand is not being met. Okay, in this situation, it can be remedied by installing a VAR generator at some load buses. So which I have said previously, when there is a voltage drop, we need to install a VAR generator or a capacitor. These buses in the load flow analysis are then regarded as PV buses with resulting solution giving the requisite value of VAR injecting at these buses. Okay, so we go to the next slide. So hopefully the previous slide is okay. Now the next paragraph is that the fact that the positive VAR injection at any bus of an interconnected system would help to raise the voltage at the bus is easily demonstrated below. So let us see how the voltage is considered. Now you consider figure 6.15, which is shown below. Okay, so you have in the figure we have a bus, we have a generator with a Thevenin equivalent resistance and Thevenin equivalent reactance connected to bus of load Vi. Okay, now we have connected a capacitor to it. Now let's see what happens. Now the so when obviously when the Thevenin voltage becomes equal to Vi if there is no power if the system is disconnected. Okay, now if we add a capacitor to it, a JQC current will from the VAR generator is injected into the bus. Okay, so the total QR or the receiving end power, receiving end reactive power is given by this equation QR equal to Vs Vr by x cos delta minus Vr square by x. Okay, Vs and Vr are sending end voltage and receiving end voltage. Okay, now with this equation can be further simplified taking cos delta equal to 1. So if we take cos delta equal to 1, the equation is simplified like this. QR is nothing but Vr by x into Vs minus Vr. Okay. Now we can see since this Vs and Vr is dependent on the value of QR, that is the total reactive power flow in the bus, we can change the we can take the Vr on the right on the left hand side. Okay, so we can see since we are considering a voltage rise for a few percent, then the modulus of Vi dash can be further approximated to Vi dash equal to Vi plus XTH by Vi into QC. Okay, thus the VAR injection of JQC caused the voltage at the ith bus to rise approximately by XTH by Vi into QC. Okay, so this is what you need to understand, that if it is connected by a VAR, the amount of VAR that has been injected increases the voltage by the XTH, that is the Thevenin's reactance, divided by the voltage into that VAR. Okay, so we have if you go to the calculation you can understand. Okay, so this is how the voltage is controlled by the generators. So this is the end of this lecture. Thank you.